Hello, my name is Salwa Faul, and I'm a PhD student at the University of Freiburg, Germany. I would like to talk about approximating bipartite minimum vertex cover in the congest model. This is a joint work with my supervisor, Fabian Kuhn. The plan of the talk is the following. In the introduction, I will present the minimum vertex cover problem and our first simple result. Then, I will talk about the state-of-the-art of the problem in the distributed setting and our main contributions. As for the next two sections, I'll explain the key ideas and algorithms that led to our main results. Finally, I conclude this presentation with some open problems. So let's start. In the minimum vertex cover problem, we are given an arbitrary graph and asked to find a vertex cover with minimum cardinality. That is, a smallest possible size subset of vertices that contains at least one node from every edge in the graph. For example, the yellow nodes of the graph on the right make up a minimum vertex cover of that graph. In this work, we study the distributed complexity of bipartite minimum vertex cover in the standard congest model. In this model, the network is modeled as an n-node undirected graph where each node has a unique order of log n bit identifier. The computation proceeds in synchronous communication rounds. For each round, each node can perform arbitrarily local computations and send one message to each of its neighbors, where the size of each message is restricted to order of log n bit. At the end, every node should know its own part of the output. So, for example, whether it belongs to the vertex cover or not. Our first contribution is a simple linear time algorithm to exactly solve the minimum vertex cover problem. While in general graphs, by a known fact, a minimum vertex cover is at least as large as a maximum matching, for bipartite graphs, Knish's well-known theorem states that equality holds there. In the proof of the theorem, a way of constructing a minimum vertex cover from a maximum matching is provided. And a direct implementation of the theorem's constructive proof in the congest model gives our first result. We will next briefly present the implementation. Assume that we are given a bipartite graph and the bipartition of the nodes into sets A and B. A vertex cover of the same size can be then found in the following simple manner. We first compute a maximum matching M star of the bipartite graph. That can be done in O of M star log M star in the congest model by running the algorithm of Ahmadi, Kuhn, and Oshman. Let A0 be the set of unmatched nodes in A. That is, nodes which are only connected to unmatched edges. And let L be the set of nodes that are reachable from A0 over alternating paths. That is, over paths that alternate between edges in the matching and edges outside the matching. By doing a parallel BFS exploration on alternating paths, starting at all nodes in A0, set L can then be computed in all M star rounds. Lastly, every node in A that was not hit by the BFS search is obviously not in L, and hence can consider itself in C star. In contrast, every node in B that was hit by the BFS search is in L, and can thus count itself in C star. It is then not hard to show that C star is a vertex cover that contains exactly one node of every edge in M star. And since, by a known fact, the size of the minimum vertex cover is at least that of the maximum matching, we deduce that C star is the minimum vertex cover of size equal to that of M star, and can be computed in O of opt-locked opt rounds in the congest model, where opt is the minimum vertex cover size. Now, we move on to talk about what's known for the distributed minimum vertex cover problem and our main contributions afterwards. When studying the distributed minimum vertex cover problem, the focus has mostly been on establishing how many synchronous communication rounds are needed to solve or approximate the problem in the less restricted local model. So solving MVC exactly on general and bipartite graphs takes theta of d rounds, where d is the diameter of the graph. Indeed, on one hand, every problem in the local model can be trivially solved in diameter time, where each node gathers all the information of the graph in order of d rounds and brute force the solution locally. On the other hand, an omega of d rounds is necessary, simply because the problem of finding an optimal vertex cover on path is equivalent to finding a two-coloring on path, where it is known that solving the two-coloring paths problem takes precisely theta of n rounds. As for the restrictive congest model, in general graphs, the best known algorithm for exact MVC runs in order of opt squared, given by Ben Bassat, Kuwar Abayeshu, and Schwartzman, where opt is the size of the minimum vertex cover. This upper bound is close to tight because of the lower bound omega tilde of n squared given by Sensor Hillel, Khoury, and Pass. On the bipartite side, we give a simple O opt log opt algorithm for solving exact minimum vertex cover, as we have seen in the introduction. As for the lower bound, an omega tilde of d plus square root of n follows from the work of Ahmadi, Kuhn, and Oshman, where in their disk paper, they prove the lower bound for the maximum matching. But the same argument also works for the minimum vertex cover problem. As things seem a bit pessimistic when working with optimal MVC, somehow expected when working with NP-hard problems, naturally things might get brighter with approximation. So here's what we know about 1 plus epsilon approximate minimum vertex cover, where epsilon is a sufficiently small constant. It was shown by Khafari, Kuhn, and Maus that the minimum vertex cover problem, and in fact, all distributed covering and packing problems, can be 1 plus epsilon approximated in time polylog n divided by epsilon in the local model. The upper bound obviously still hold for the bipartite case. However, due to the work of Goose and Swamila, it was further proved that there exists no sublogarithmic time approximation scheme for bipartite vertex cover, even for bipartite graphs of maximum degree 3. As the complexity of the distributed minimum vertex cover problem in the local model is now understood quite well, there has recently been increased interest in also understanding the complexity of the problem in the more restrictive congest model. However, in the congest model, for better than a 2 approximation, nothing faster was known than the bounds we have just seen for computing an exact solution in the general and bipartite case. We note that the distributed 1 plus epsilon approximations for MVC and related problems quite heavily exploit the power of the local model, thus cannot be used for congest. So in this work, we focused on the bipartite case and asked ourselves, can we efficiently get a good approximate minimum vertex cover in the congest model? Yes, and this is our contribution. We give polylogarithmic time algorithms for both the randomized and deterministic cases, where both algorithms run in order of polylog n divided by epsilon rounds, with the randomized complexity being faster, and for a fixed epsilon, matching the logarithmic lower bound by Goose and Swamila mentioned above. To achieve our main results, polylogarithmic time algorithms for approximating bipartite minimum vertex cover, We will first show how to solve the problem in time linear in the diameter. Then, how one can use that to reach faster algorithms. The core of the algorithm that will help us achieve an approximate bipartite minimum vertex cover in time linear in the diameter is a method to transform an approximation solution of the maximum matching problem into an approximate solution of that of the minimum vertex cover on bipartite graphs. And it will take order d plus k rounds in the congest model. But this matching needs to have an extra property, a guarantee that no short augmenting paths exist in the graph. And by short augmenting paths, I mean augmenting paths of length at most 2k minus 1. Recall that given a matching, an augmenting path is a path that starts and ends with unmatched vertices and alternates between matched and unmatched edges. Also note that by a known fact, a matching with no short augmenting paths is an approximate one, but the converse is not necessarily true. We will next show how our approximation scheme works by adapting the constructive proof of Kinish's theorem mentioned earlier. To simplify things, let's explain the algorithm while running an example here on the left. Let k be a positive integer parameter. And for our example, we choose k to be equal to 2. Let G be a bipartite graph. The bipartition, A and B, can be easily computed via constructing a spanning tree in order of d rounds. We also assume that we are given a matching with the guarantee that no short augmenting paths exist. Hence, for k equals 2, any existing augmenting path has to be of length at least 5. First, we define A0 to be the set of unmatched nodes in A. Next, for every I from 1 to k, we define the sets AI and BI in the following manner. BI is the set of nodes in B that are reachable from some unmatched node in A0 over a shortest alternating path of odd length 2i minus 1. Similarly, we define the sets AI for every I with the difference that the shortest alternating path should be of even length 2i. Computing the BIs and AIs can be easily implemented in the congest model by running the first 2k iterations of parallel breadth first search over alternating paths starting from each unmatched node in A0. And depending whether the node is in the odd or even level iteration, it will join the corresponding set BI or AI respectively. We demonstrate how this construction works on our example, where we only need to run the first 4 rounds of parallel BFS starting from the nodes in A0. Notice that the nodes that have not been hit by a BFS don't join any new set. The time required to do this parallel BFS and obtain the BIs and AIs is obviously order of k rounds. Now, we define I star to be some I in the set 1 to k, such that the size of the set BI attains its minimum. So I star is equal to 2 in our example here. Computing I star in step 4 can be done in order d plus k rounds by using the already computed BFS spanning tree and a simple pipelining scheme. One can compute the sizes of all the sets BI and determine the index I star of the smallest such set. Lastly, for step 5, the algorithm outputs the set Ci star that contains from A all the nodes that are not in A0 till AI star minus 1. And from B, it takes in all the nodes from B1 till BI star. So the gray part in our example here will then represent Ci star. Of course, the root of the tree can broadcast I star to all nodes via the BFS tree in time order of D rounds. Then nodes can decide whether to join Ci star or not accordingly. Therefore, the overall time complexity of the algorithm is order D plus K rounds as claimed. Now, to prove that Ci star is our desired approximate vertex cover, first, we show it is a vertex cover. Indeed, every edge is incident to at least one node from Ci star. So, from the gray part, else there would exist an edge connecting a node in A from the top left outside Ci star to a node in B from the bottom right outside Ci star. An example is this red edge. But regardless whether this edge is matched or unmatched, one can see that such edge cannot exist due to the way we constructed our sets AI and BI via the parallel BFS. Hence, Ci star is a vertex cover. To finally show it is an approximate vertex cover, we need the following two observations. The first observation is that each set AI is exactly the set of nodes that can be reached over the matching edges from nodes in BI. Hence, for each of the I's, we have the size of set AI equal to that of BI. So in our example, the size of A1 is equal to that of B1. Similarly, A2 is equal to B2. The second observation is that all nodes in the sets B1 up to BI star are matched nodes. So in our example, B1 and B2 contain only matched nodes. Else, there would exist a short augmenting path from a node in A0 to an unmatched node in B. Moreover, and this is due to how we define Ci star, from every matching edge, our vertex cover Ci star contains exactly one node except for the matching edges that connect BI star to AI star, where BI star is the smallest of the BIs. And hence, by simple calculation, it's at most a 1/k factor of the matching. Using these two observations, one can do the math and prove that Ci star is a 1 plus 1/k approximate vertex cover. From here, there are really two challenges that remain for eventually getting faster polylogarithmic algorithms. One, we need to efficiently get this matching that we have assumed so far, which guarantees that no short augmenting paths exist. We do that, and we have an algorithm that solves our problem in time linear in the diameter. The second challenge is that the diameter might be large, and small diameter is needed in order to run our previous algorithm and eventually approximate bipartite MVC efficiently. For the first challenge, if we allow randomization, then there exists an efficient congest algorithm that gives a matching in bipartite graphs with the desired guarantee. The algorithm is given by Lotker, Pachemir, and Petty. In combination with our key approximation scheme, we are able to directly get a randomized algorithm that for a fixed integer parameter k approximates bipartite minimum vertex cover in time linear in the diameter as promised. As for the deterministic case, we run a polylogarithmic time approximate maximum matching algorithm in the congest model by Ahmadi, Kuhn, and Oshman. Unfortunately, this algorithm does not guarantee that at the end there are no short augmenting paths. We resolve this by first removing a small number of nodes of the graph such that the remaining graph has no short augmenting paths. Thus, we can apply our key approximation scheme on the remaining graph to get a vertex cover there. Eventually, these removed nodes can be added back to get a vertex cover of the original graph. Now, the problem of finding a small set of nodes to get rid of all short augmenting paths can be phrased as a minimum set cover problem, which we can approximately solve by an efficient algorithm in the congest model. To overcome the second challenge, we decompose the graph into clusters of small diameter by adapting existing fast, low diameter graph clustering algorithms. Where for the randomized, we use Miller, Ping, and Zeus low diameter clustering. And for the deterministic case, we modify the recent polylogarithmic time network decomposition of Rajan and Khafari. We can then solve the problem inside the clusters using our linear and diameter time algorithms. Note that we need to do this adaptation to get a clustering with specific properties. This will help us deal with edges between clusters that might be left uncovered. Therefore, we have seen how we can use the time linear and diameter algorithms together with existing adapted low diameter graph clustering algorithms to obtain polylogarithmic time approximation schemes for the minimum vertex cover problem in the congest model, both deterministic and randomized. We can now conclude this presentation. Recall that for computing an optimal vertex cover on general graphs, it is known that omega tilde of n squared rounds are necessary in the congest model. It is therefore an interesting open question to investigate if it is possible to approximate minimum vertex cover within a factor smaller than 2 for general graphs in the congest model, or to even understand for which families of graphs this is possible. I would like to thank you for your attention.